Welcome at the 7th lecture of the High Resolution Imaging course. Today is the final lecture of the series on scanning electron microscopy. Before we start out, let's look a bit back at the key concepts that we learned in the past two lectures. So first, we have seen which signals are generated in an SEM and from where in the sample they originate. We've looked at secondary electrons and we learned that they mostly give topography contrast. And we also looked at backscattered electrons. And we've seen that the contrast given by the backscatters mostly comes from differences in atomic number in the material composition. We looked a bit at both kinds of detectors and the differences in there. And we looked at charging resulting from the electron injection in the sample and the fact that electrons are also ejected out of the sample, constituting our signal. And the imbalance in those two processes determines whether or not the sample might charge. Starting from there, we also looked at sample preparation for SEM, which is very important if we look at biological samples. And we need to prepare our sample for the scanning electron microscope, which includes fixation, dehydration, embedding, sectioning, staining, adding labels, or adding things that generate contrast in electron microscopy. So it's very invasive. We've looked at the difference between cryofixation, which is maybe better for native state preservation, versus chemical fixation, which is amenable to larger samples or human tissue. And we've seen the wide variety of sample preparation diagrams that are existing in electron microscopy. So you also played around a bit with the homework assignment and learned a little bit about scales in electron microscopy. So as a starting point for today, we will look a bit further into the accessible scales with imaging and how we can go to large-scale imaging in 2D and also to extend electron microscopy to the third dimension. Also, at the end of today's lecture, we will look at correlative light electron microscopy, where we try to combine information from light or fluorescence microscopy with that we can obtain for electron microscopy. We've learned that the electron beam penetrates a very limited volume in the sample, the depth of which depends on the energy of the incoming electrons. Most of the signal is generated just below where the electron beam hits the sample. So we can think of the electron microscopy as a nearly 2D technique, especially for biological samples where we use low energies, 1 to a few kilo-electron-volt. So in essence, we scan either a thin section taking out of a sample, or we scan the surface of a macroscopic object. Let's first look a bit at how this image generation goes. Okay? So we look back at the concept of scanning. So scanning means we position our electron beam at one position on the sample, we generate a signal, and when we have collected sufficient amount of signal, we go to the next position. So the time spent at one individual pixel is what we call the dwell time. So in practice, the electron beam does not step from one pixel on the sample to another, but continuously sweeps over the sample, and the detector collects signal for a limited amount of time. So the time that the detector collects signal in relation to the area scanned by the sample during that time is what determines a pixel in practice. But we can still think about this as stepping from one pixel to the other. So say our dwell time is 20 microseconds, which is a realistic value for an electron microscopy experiment. And suppose we scan an image of 1024 by 1024 pixels. This means that we have a pixel dwell time on the order of 20 times 10 to the minus 6 seconds, and we have to record about 10 to the 6th pixels, slightly more. So this will take approximately 21 seconds, slightly more than 20 seconds, say 21 seconds. Now suppose our pixel stretches an area of 1 nanometer by 1 nanometer. So we do really high resolution scanning electron microscopy. This means with the 1024 by 1024 pixels that we scan an area which is approximately 1 micrometer squared. So 1 micrometer squared can be recorded quite quickly, only 21 seconds, but it's a very small area. Say we would like to collect the high resolution data over a larger area, about 100 micrometers squared. This would then result in a scan time of 210,000 seconds, which is about 58 hours. And that's only an area of 100 by 100 micrometer. So we see that we can record an electron microscopy image very quickly, but it's always a very limited area, which is intrinsic to the fact that we do high resolution scanning. Of course, we should also realize at this point that if we would choose a 3 times larger pixel size, we could do 9 times faster imaging, but we scan with a lower resolution. Note also that if we bring back the resolution, so if we lower the resolution of our measurement, it might mean that we can use more current. We can allow a little bit larger probe size, so we can add more current, so the imaging may also be accelerated in this way. But it's good to have these dimensions in your head and be able to do back-of-the-envelope calculations on imaging acquisition times. Now here you see an example where we record the full fields of view in order to generate a larger tile. The calculation that we just did suffices to get a rough feeling for the amount spent in recording such a larger tile. However, we also should bear in mind that there's overhead in the measurement. We need to include stage moves to cover the entire 100 by 100 micrometer area. We may need time for refocusing the beam in an automated fashion, and we also need to record a bit of additional area in order to allow for stitching all the individual images together in one big tile. So we got a bit of a sense for the time spent in covering a large area. So for a long time, electron microscopy mostly consisted of taking single images, so a snapshot of a sample. Typically, a user would sit behind the microscope, maybe together with an operator, looking at the sample, how it's generated with the microscope, but then only recording images from selected areas. Now, with recent advances in automation and autofocusing of microscopes, large area imaging has become more in use. And we've seen before that scanning mostly involves two-dimensional images, so a section or a surface of a sample. Now, people have also attempted to go to three-dimensional imaging. And there's in general 2 approaches that we can do here. So we've seen that the process of sample preparation for electron microscopy involves sectioning a larger block of sample. Now, if we would section that block and we would collect the first section, then collect the second section, and each following section in serial order, and scan those also with reference to the order in which they are scanned, then we could reconstruct the 3-dimensional image afterwards from all the individual 2-dimensional tiles. Now that's one approach. This approach we call serial sections. The other approach is that we load the entire block in the scanning electron microscope, then image the upper face of the block. We know that we image only a very small depth in the sample, so it's basically an image of the top side of the block. And then we slice off a thin section and image the upper face of the block. Again, this is what we call block face imaging. Now, for both approaches, there are a few techniques in use. And we're going to look at this in a bit more detail. So the first one, serial sections, has already been around for quite some time for transmission electron microscopy imaging. It's good to know that transmission electron microscopy has been the prime technique for use in biology. Scanning electron microscopy has only reached high-resolution imaging in recent years and also has come more in use due to advancements for large-scale and volume imaging. So serial sectioning has been around for quite some time in transmission electron microscopy. And you see a schematic indication here. So the water bath you see on the left has the serial sections floating in order, and they are picked up on a grid which has an elongated slot in there. Now the images are scanned by transmission electron microscopy, and as we will see in the later lectures by Ari and Jacobi on transmission electron microscopy, as opposed to a scanning microscope, a transmission microscopes illuminate a larger area, so this can intrinsically go a little bit faster. However, the amount of sections that we can place on a grid is limited. A second approach is block face imaging in scanning electron microscopy. And in this technique, we use a microtome that is placed inside the vacuum chamber of the scanning electron microscope. So you see that depicted here. So the electron beam comes from the pole piece that you see above the sample in the image. It scans over the surface, generates electrons which are collected and constitute an image of the upper surface of the resin block. After the full surface has been collected, the diamond knife comes in, cuts off a thin section which falls off the block, the knife is retracted and the beam scans the upper face again. And by repeating this process, we can collect a three-dimensional image. So here the resolution along the z-axis, just like in the serial section TEM approach, is limited by the thickness with which we can cut. Now another approach for block phase imaging in scanning electron microscopy is if we use a so-called dual beam system, a microscope that has a pole piece generating an electron beam, but also has another column which generates a focused ion beam. The ion beam, of course, consists of ions which have a much larger mass than the electrons that are in the electron beam. Now this higher mass means that they penetrate less inside the sample, but also interact much stronger and actually sputter away material from the surface. So in this way, after recording an image of the upper face of the block, just like we do with the block phase imaging with a microtome, we come in with our ion beam, we scrape off, we mill away the upper face of the block, and we repeat the process of imaging with the electron beam. Now the advantage of the ion beam is that we can mill a very thin layer. And the thickness of the layer can go to 5 nanometer. This means that we can get more or less isotropic voxels. And so we can set the resolution in XY with this electron beam scanning to 5 nanometer, and then the pixel dimension in Z from the FIB milling can also be 5 nanometer. So this is a big advantage, and actually this is the technique which generates the highest resolution information in 3D. Of course, like we've seen for the calculation in scanning a 2D image, also here a higher resolution in Z means that the process goes much slower, so the throughput is lower. Now the final approach is serial section imaging in scanning electron microscopy. So the process goes conceptually similar as to a TEM, apart of course that the imaging mechanism is different. We don't do transmission imaging, no phase imaging, but we scan the beam over the sample. So the scanning can maybe go a bit slower. But one of the advantages is that we can add much more samples inside the electron microscope. So much more stripes of sections can be loaded. So you see in the image for serial section imaging in SEM that it's conceptually similar to that for the TEM, but there's a difference here in that we don't have the grid with the oval slot for having the serial sections, but this system actually depicts a water bath where a tape is running through the water bath, picking up the sections, and afterwards this tape can be cut into parts stuck to a larger area, wafer or sample holder, loaded in the electron microscope, and in this way we can load many individual sections at once in the system. There's also alternative variants that do this, for instance by adding magnetic adhesion to each section and labeling each section so that the serial order can be reconstructed afterwards, but in essence all these approaches are similar. It's good to realize that this example also suffices to illustrate that while the acquisition of images is a major limiting factor in determining the throughput and thus the size of the volume that can be accessed, this is not the only limiting factor. And we have to realize here that if we go to a large volume, which consists of thus of a large amount of sections, all these sections have to be cut in advance, and we might need an automated way of doing this. Okay, let's look at an example. So here you see an example from a review paper from 2012, and in the upper row you see images which are XY images, so these are the section images or the upper face of the block. From left to right we first see serial section TEM, then we see serial section SEM example, we see serial block face example where we do a microtome, and the final one is a FIB-SEM image. Now the lower row depicts the XZ images, so this comes from stitching the images below each other. And we can now clearly see in the first three images, so the serial section approaches and the block phase, that the resolution in Z is limited, while the FIB-SEM image in XZ looks much more smooth due to the high resolution along the axis. So remember that it's nearly isotropic resolution. We can also see, if we look carefully, that the FIB-SEM image looks particularly black-white. And this is a bit common for block phase approaches. In general, in order to generate sufficient signal from the block, and in order to avoid charging, which may be a serial issue in block phase imaging, the amount of staining material and fixation material that is used in sample preparation for block phase imaging may be quite high. And this then results in a very black-white type of contrast that we have in imaging. And it's good to realize that grayscale is important in interpreting biological images. Having said that, a particular advantage of FIB-SEM over serial block phase imaging with a microtome can be that the consecutive order of imaging with electrons and milling with ions can also mitigate the charging artifacts a little bit, as opposed to the diamond knife, where every time the block is imaged, it is done with a negative charge. So in the beginning of this lecture, we got a feeling for the time spent for imaging to the sections. In the same review paper as where I got the previous images from, the authors also extended typical parameters for electron microscopy acquisition with the 4 different techniques to what would happen if we would image a mouse cortical column of specific dimensions. So here you see in the first row that I marked that, of course, an important aspect is whether or not the machine can run in an unattended fashion. So do automated acquisition without the operator having to sit behind the machine for days or longer. And so this is a particular example of an SEM, is that it's much more simple to automate. Now in the lower marked area we see typical numbers. And we can see that the total acquisition time for this mouse cortical column amounts to hundreds of days of unattended acquisition. And so this is an incredible burden on electron microscopy. We should also realize, and we've already seen, that also the sample preparation, particularly for serial sectioning, may be a bottleneck that needs an automated solution. We're now also generating an incredible amount of data. And recall that in the calculation that we started this lecture with a 1 nanometer pixel size, we had a 1024 by 1024 pixel image. So this may be a 16-bit image. And recall that that only covered 1 square micrometer. So that means that for 3D imaging, the amount of data that we generate easily runs into multiple gigabytes, terabytes, or in future maybe even to petabyte sizes. This is a serial challenge for annotation and handling the data. Now we've seen the several approaches to 3D imaging. And each of these approaches has its particular advantages and disadvantages, which you should be able to understand where they come from based on the knowledge that we now have on electron microscopy. So first, the serial block phase imaging. Just like the FIB-SEM and the microtome imaging, a serious problem may be that, of course, the block is destroyed during imaging. In the FIB-SEM, each section is really milled away and the material is gone. In the situation with the microtome, of course, the section is scraped off, but then falls on the bottom of the vacuum chamber, and there's no chance of reusing this again. We've also seen that in both approaches, there's the risk of charging the entire block. So it would be beneficial if we have some means of getting this charge away, and people have done attempts in this direction by flushing with nitrogen after each imaging step, which may mitigate the surface charging a little bit. Also, we have seen that the fixation and staining is typically very strong and may lead to a kind of black-white contrast in our images. Also, and particularly for the FIB-SEM, while an advantage is that we can do high-resolution 3D imaging, of course this means that the process for covering larger volumes becomes slower. Then serial sections may seem a good advantage, but also here there's particular disadvantages to this approach. While in the FIB-SEM we always image the area before it's being sectioned, in serial sections we do the sectioning in advance. So based on these considerations, we may think that serial sectioning is actually the go-to approach. And yes, with serial sectioning, all the sections are kept intact after imaging. So we can think of a strategy where we first do low magnification imaging of all the sections to identify the areas for high resolution imaging, so that we go through the volume little bit faster. This is an approach that actually has been used to cover the brain of a zebrafish and would never be possible with a block phase approach. However, there's also particular disadvantages to the serial sectioning. So you have to realize that when you section a block, you may compress and stretch a little bit due to the action of the knife in the material. So this means that every section may be distorted in a slightly different fashion as the next one. So there's a large burden on doing the 3D reconstruction, which may involve warping the data set from section to section. Of course, in the block phase approaches, in the FIBSEM, there is no sectioning, and in the microtome sectioning, the upper face is always imaged before actual sectioning takes place. So this issue plays less of a role as it does in the serial sectioning. However, we will see later that the serial sections also may have a particular benefit if we look at combinations with fluorescence microscopy. I already want to point out here that serial sectioning may have an advantage also in terms of combination with light microscopy, particularly with fluorescence, where a disadvantage of the block phase approaches is that we typically need quite strong staining and fixation. And we will see later in the session about correlative microscopy that this has a large impact on the ability to keep fluorescence in the block.